So for this video, we'll mostly be looking at this figure from your textbook, which is showing all of the molecular orbitals for the second row of the periodic table up through fluorine. And we'll be looking at sort of the properties here. And so we've looked at one of these already, lithium, the lithium dimer. And we're ignoring the 1s electrons because they mostly are localized on the individual nuclei, and the bonding and anti-bonding kind of add up to nothing overall. And it's the valence electrons we care about. And so for lithium dimer, right, we get something that has two bonding electrons, and the sigma G is a bonding orbital. And so this has a bond order of 1. So we can kind of list the bond orders down here. As we go to beryllium dimer, add 2 more electrons, we get a bond order of 0. And at least at this first approximation, because we have an equal number of bonding and anti-bonding electrons, this first approximation, we think this is very similar to helium, where it doesn't really form a bond. And according to this level of theory, that's true. We'll talk about this probably in class, maybe not in a video, but actually beryllium does form a dimer. And it's something that my postdoctoral advisor studied this molecule, which has very interesting properties. So something to think about. Anyway, but to this level of approximation, beryllium dimer doesn't form. And when it does form, it doesn't form a very strong bond, even when it does form. Boron dimer. So now our s electrons down here are kind of canceling out, and so we'll get a bond order of 1 because we have 2 electrons in these pi bonding orbitals. As we go to carbon dimer, we now have 4 electrons in bonding orbitals, so that has a bond order of 2. Nitrogen has a bond order of 3, right? It has a triple bond in this, and so far nothing's very different from what you'd expect from, say, drawing a Lewis structure or something like that. As we go to oxygen, now we have some anti-bonding electrons, and you can see the relative ordering of these energies is changing as we go across the periodic table. In particular, this orbital right here, this sigma bonding orbital, starts higher in energy and keeps decreasing relative. All of these up here, including these anti-bonding orbitals, are also doing this. But it leads to a slight change, particularly going from nitrogen to oxygen. I don't particularly care if you remember where this happens. I always forget, but we see that this orbital switches to down here. Anyway, the important point is that we have a bond order of 2 for oxygen. Oxygen is a double bond. And as we get to fluorine, because we have more electrons in anti-bonding orbitals, we're back to a bond order of 1. And this picture that we have corresponds with the relative bond lengths and bond strengths as we go across the periodic table. So one of the most interesting things about this is if we look at oxygen, we notice that according to the predictions of molecular orbital theory, oxygen has 2 unpaired electrons. And if we have unpaired electrons in a molecule, that means it is paramagnetic. And so this molecular orbital theory predicts that oxygen is paramagnetic, meaning that it can be attracted by magnetic fields. And this is one of the coolest things I think that you can do. You can take liquid oxygen, and if you pour it between a very strong magnet, you can actually get it to stick there. And there's actually a video of this. I'll probably put a link to it on the Moodle page for you to look at. Right, and so we see these patterns as we go across the periodic table, and this is these different combinations of atomic orbitals coming together to form molecular orbitals. One other thing that we'll look at in the next video is how do we know that this is actually really happening? So we have some evidence from the paramagnetism of oxygen. How do we know these relative orders of orbitals and things like that? And so our experimental evidence comes from spectroscopy. In particular, we'll be looking at a type of spectroscopy called photoelectron spectroscopy, where we can use light to eject electrons, similar to the photoelectric effect. And the amount of kinetic energy of those electrons tells us about the energies of the orbitals that they come from.